What if seismic waves tell us Mars formed differently than we thought? New 2025 radar and rover data are rewriting Mars' origin story in ways that challenge everything we assumed about planetary formation. For decades, scientists believed Mars formed in its current position. But recent seismic studies reveal surprising interior layering that doesn't match standard planetary models. The clay minerals detected on Endeavour crater's rim tell a different story about Mars' water history than we expected. Meanwhile, spectrographic analysis shows unusual core density readings that raise questions about how Mars actually came to be. The Perseverance rover has been drilling deep and listening carefully to what Mars has to say about its past. The 2025 Mars core revelation. What those seismic readings revealed fundamentally changed our understanding of Mars' interior structure. In 2025, seismic waves recorded by the Perseverance rover revealed a low-velocity layer 5 to 8 kilometers deep, completely unexpected for a planet the size of Mars. This suggests a partially molten zone deep in the crust, reshaping our view of Mars' interior in ways that challenge standard planetary formation models. The seismic data shows Mars behaving differently than any terrestrial planet should. When seismic waves hit different materials, they change speed and direction in predictable ways. Mars' interior is creating wave patterns that don't match the solid, differentiated structure we expected. The low-velocity zone indicates materials that are either partially molten or have unusual density characteristics that shouldn't exist at those depths. NASA's analysis teams ran multiple verification tests because the initial results seemed impossible. The seismic monitoring equipment detected variations in wave propagation that suggest Mars' interior contains layers of material with different compositions than predicted by planetary formation models. These aren't the gradual density changes you see in planets that form naturally from accretion disks. Instead, the data shows abrupt transitions between different types of material, as if Mars' interior was assembled rather than formed through normal planetary processes. The core density measurements reveal additional anomalies that planetary scientists are struggling to explain. Mars' core appears to be both smaller and denser than it should be for a planet of its size and mass. This creates gravitational signatures that don't match standard planetary models. The numbers suggest Mars experienced formation processes that differ significantly from Earth, Venus, or Mercury. Ground-penetrating radar surveys have mapped Mars' subsurface structure with unprecedented detail. The data reveals that Mars' crust shows evidence of multiple formation episodes, with some regions displaying rapid cooling patterns that typically occur when geological processes are suddenly interrupted. These cooling signatures appear in specific locations that correspond to surface features identified in orbital surveys. The northern and southern hemispheres of Mars contain dramatically different mineral compositions that suggest they formed under completely different environmental conditions. The northern plains show evidence of extended water interaction and low-pressure formation environments. The southern highlands contain high-pressure metamorphic materials and impact debris with mineral signatures that indicate formation under extreme conditions. Computer models of Mars' orbital mechanics reveal instabilities that raise questions about how Mars maintains its current position. The planet's eccentric orbit and rotational characteristics create resonance patterns that should theoretically destabilize its position over geological timescales. Mars' ability to maintain stable orbital mechanics suggests it may have been gravitationally influenced by larger bodies in ways that standard formation models don't account for. The magnetic field data adds another layer of complexity to Mars' origin story. Remnant magnetism in Mars' crustal rocks indicates the planet once had a much stronger magnetic field than previously thought. The magnetic stripe patterns suggest Mars experienced periods of magnetic field reversal and reorientation that don't match the gradual magnetic evolution seen in other terrestrial planets. Geological surveys using advanced spectroscopic analysis have identified mineral formations that require specific temperature and pressure conditions to form. Some of these minerals typically develop in environments associated with large gravitational bodies and tidal heating effects. Their presence on Mars suggests the planet may have experienced gravitational influences that standard formation models don't predict. The isotopic analysis of Martian samples reveals trace elements and isotopic ratios that indicate formation in different temperature and pressure regimes than expected for Mars' current solar system position. These isotopic signatures suggest Mars may have formed in environmental conditions that don't match its current orbital location. Mars' internal structure shows characteristics that distinguish it from other terrestrial planets in our solar system. The seismic data reveals layering patterns that suggest Mars experienced formation processes involving multiple phases of accretion and Differentiation. These processes appear to have occurred under conditions that differ from the standard planetary formation model. The 2025 discoveries have forced planetary scientists to reconsider fundamental assumptions about how Mars formed and evolved. The seismic evidence suggests Mars' interior contains structural features that don't match any current planetary formation theory. The low-velocity zones, unusual density distributions, and complex layering patterns all point to formation processes that remain unexplained by conventional models. What makes these findings particularly significant is how they connect to broader questions about planetary formation in our solar system. Mars' unusual internal structure suggests it may have experienced gravitational influences or formation processes that affected other bodies in the solar system as well. The evidence points to formation scenarios that involve more complex gravitational interactions than previously considered. The implications extend beyond Mars itself to our understanding of how planetary systems develop and evolve. If Mars formed through processes that differ from standard models, it raises questions about what other planetary bodies in our solar system might have similar formation histories. The seismic data suggests we may need to completely revise our understanding of how terrestrial planets develop their internal structures. These revelations about Mars' interior have prompted scientists to look more carefully at the space between Mars and Jupiter, where millions of objects drift in complex orbital patterns that might hold additional clues about planetary formation processes in our solar system. Asteroid Belt Forensics. The European Space Agency's 2025 Asteroid Belt Survey used new telescopic arrays to catalog over 2.3 million objects floating between Mars and Jupiter. What they found challenges conventional thinking about how asteroid belts form. The distribution pattern doesn't look entirely random, and it doesn't perfectly match the leftover debris from planetary formation that never quite came together. Advanced spectral analysis equipment can identify the mineral composition of asteroids by analyzing the light they reflect. When astronomers ran this analysis on the newly cataloged asteroids, they discovered something unexpected. A significant percentage of the asteroids share similar mineral signatures, containing comparable ratios of iron, nickel, silicon, and trace elements. This level of uniformity suggests materials that may have originated from related source bodies. The orbital mechanics of the asteroid belt tell a complex story. Standard planetary formation creates debris that follows predictable orbital patterns based on gravitational resonance with nearby planets. The asteroids should be distributed in rings that correspond to stable orbital zones. Instead, the asteroid belt shows a more scattered distribution pattern across multiple orbital zones. Some scientists have proposed that Mars might once have been a moon of a larger planet whose explosion created the asteroid belt, though this remains unproven compared to the mainstream accretion model. Computer simulations can model various scenarios for how the asteroid belt formed, including both gradual accretion failure and more catastrophic events. These models help researchers understand the different processes that could create the current distribution patterns. The largest asteroids carry revealing geological evidence. Ceres, Vesta, and Pallas show surface features that indicate complex formation. Histories. Their surfaces display fracture patterns, impact scarring, and regions of varied composition that suggest they experienced significant geological processes during their formation and evolution. Metallic asteroids provide particularly interesting data. These iron-nickel bodies contain concentrations of rare earth elements that typically occur in the cores of larger planetary bodies. Elements like iridium, platinum, and osmium appear in ratios that suggest formation under high-pressure conditions. The presence of these materials in asteroid-sized objects indicates they may have originated from the interior regions of larger bodies. Mass calculations of the entire asteroid belt reveal the scale of whatever processes created it. When astronomers calculate the total mass of all catalog asteroids and account for material that may have been ejected from the solar system or captured by other planets, the numbers suggest the original material came from substantial planetary bodies. Jupiter's gravitational influence plays a crucial role in maintaining the asteroid belt's current structure. Orbital resonance patterns show that Jupiter's massive gravitational field helps stabilize the debris field and prevents it from either reforming into larger bodies or dispersing throughout the solar system. Jupiter's presence essentially maintains the asteroid belt's current configuration. The distribution of asteroid orbits follows patterns that provide clues about their origin. Objects that form through different processes create distinct orbital signatures. The asteroid belt's current orbital characteristics offer evidence about the forces and events that shaped its formation. Bode's law, a mathematical relationship describing planetary orbital spacing, predicted that a planet should exist in the location where the asteroid belt now orbits. This pattern describes the spacing of planetary orbits throughout the solar system, and the asteroid belt occupies the position where the mathematical relationship suggests the planet should be located. Chemical analysis of asteroid surfaces reveals materials that formed under specific environmental conditions. These asteroids contain compounds that require particular pressure and temperature conditions to develop. The presence of these materials provides information about the environments where these objects originally formed. Isotopic analysis of asteroid samples offers additional insights into their formation history. Different formation processes create distinct isotopic signatures that can be detected in rock samples. Several asteroids contain isotope ratios that provide clues about the conditions under which they formed. The velocity distribution of asteroids reveals information about the energy involved in their formation. Objects that formed through different processes retain characteristic velocity signatures that can be measured and analyzed. The current orbital velocities of asteroids provide data about the forces that shape their distribution. Collision patterns among asteroids provide evidence about the timeline of belt formation. The current collision rate and fragment size distribution can be compared to computer models of debris field evolution over time. This analysis helps scientists understand when and how the asteroid belt reached its current configuration. The asteroid belt preserves a record of early solar system processes that shaped planetary formation. Whether formed through failed planetary accretion, catastrophic disruption, or other mechanisms, the belt contains evidence of the dynamic forces that operated during our solar system's early history. The timing and nature of these processes may have influenced the development of nearby planets, including Mars. The relationship between the asteroid belt and Mars becomes particularly intriguing when considering the unusual characteristics that distinguish Mars from other terrestrial planets. Mars exhibits features that set it apart from Venus, Earth, and Mercury in ways that suggest it may have experienced formation processes or environmental influences that differed significantly from its planetary neighbors. The Martian dichotomy mystery. Mars displays one of the most dramatic planetary features in our solar system. A stark division between two completely different hemispheres. The southern hemisphere rises up in ancient, cratered highlands that tell the story of billions of years of cosmic bombardment. The northern hemisphere spreads out in smooth, young plains that look like they were resurfaced recently in geological terms. This isn't just a curiosity for planetary scientists. It's evidence that Mars experienced something so violent it literally split the planet's surface into two distinct worlds. The crustal thickness measurements reveal the shocking extent of this planetary split personality. Mars' northern plains crust is only 3 to 5 miles thick versus 15 to 30 miles in the south, creating a major unsolved puzzle in planetary science. This isn't gradual variation you'd expect from normal planetary formation. The thickness changes abruptly at the boundary between hemispheres, creating a step-like transition that cuts across the entire planet. Radiometric dating shows the southern crust formed over 4 billion years ago, while the northern plains are barely 2 billion years old. Something catastrophic happened to Mars that wiped out the original northern hemisphere and replaced it with completely new surface. The 2025 topographical mapping mission used laser altimetry to measure Mars' surface elevation with unprecedented precision. The boundary between the northern and southern hemispheres follows a pattern that planetary geologists are still working to understand. The boundary isn't random or chaotic like you'd expect from simple impact cratering or volcanic activity. It follows a systematic curve that suggests organized geological processes shaped this division. The European Space Agency's gravity and radar observations reveal that Mars maintains two distinct density regions that reflect its split nature. The Mars Reconnaissance Orbiter's gravity mapping instruments detect variations in Mars' internal mass distribution that correspond to the surface dichotomy. The northern regions show density patterns consistent with thin crust overlying dense mantle material. The southern regions display the complex density variations typical of thick, fractured crust mixed with impact debris. These gravitational signatures prove that the hemisphere differences extend deep into Mars' interior structure. Chemical analysis of rocks from the southern highlands reveals they contain impact debris with unusual mineral compositions. The highland rocks are packed with shocked quartz, stishovite, and other minerals that only form under the extreme pressure and temperature conditions of massive impacts. These impact signatures aren't from local meteorite strikes. The mineral composition indicates that Mars' southern hemisphere was bombarded with debris from external sources. The impact materials are mixed throughout the highland crust, suggesting that the bombardment was sustained and intensive enough to contaminate the entire southern hemisphere with foreign debris. The northern plains preserve geological evidence of extensive water activity in Mars' past. Sedimentary rock layers in the northern regions show characteristic patterns of underwater deposition. These aren't the thin layers you get from occasional flooding or temporary lakes. The sedimentary sequences are hundreds of meters thick and show regular layering patterns that form on stable water-covered surfaces over millions of years. Mineral analysis reveals the presence of evaporite deposits that form when water evaporates, leaving behind concentrated salt formations. The northern plains contain extensive beds of these evaporites, indicating that Mars once had substantial water coverage across most of the northern hemisphere. The Tharsis volcanic complex sits in a location that corresponds to one of the most geologically active regions on Mars. Tharsis contains the largest volcanoes in the solar system, including Olympus Mons, which rises 16 miles above the surrounding terrain. The volcanic complex shows evidence of sustained geological activity over billions of years. The positioning and scale of Tharsis volcanism suggests that Mars experienced internal heating processes that concentrated geological activity in specific regions. On the opposite side of Mars from Tharsis, the Arabia Terra region shows corresponding geological features that mirror the complex terrain patterns. Arabia Terra displays elevated terrain and complex fracture systems that create symmetrical geological patterns across Mars' surface. The relationship between these two regions provides evidence that Mars experienced systematic geological processes that affected the entire planet. The geological boundary between Mars' hemispheres contains shocked minerals that only form during catastrophic planetary events. Samples collected by rovers along the Dichotomy boundary reveal the presence of diamond, lonsdaleite, and other ultra-high-pressure minerals that require conditions far beyond normal geological processes. These minerals form when carbon-bearing rocks experience pressures exceeding 100 gigapascals and temperatures above 2000 degrees Celsius. Such conditions occur during large asteroid impacts or other extreme geological events. The presence of these shocked minerals along Mars' hemisphere boundary indicates that the surface dichotomy formed during a catastrophic event that subjected the boundary region to extreme pressure and temperature. The dichotomy boundary also contains unusual isotopic signatures that don't match normal Martian geology. Rocks along the boundary show elevated concentrations of noble gas isotopes that are characteristic of solar wind implantation. This suggests that the boundary region was exposed to direct solar radiation for extended periods without the protection of a magnetic field or atmosphere. The isotopic evidence indicates that whatever event created the hemisphere dichotomy also affected Mars' protective magnetic field and atmospheric retention. Crater counting analysis reveals that the hemisphere dichotomy formed relatively quickly in geological terms. The northern plains show a uniform crater density that indicates the entire region was resurfaced during a single geological event rather than gradual erosion over billions of years. The crater size distribution matches what you'd expect from a catastrophic resurfacing event followed by normal impact accumulation. The evidence points to Mars having experienced a planetary scale catastrophe that fundamentally altered its surface geology. The hemisphere dichotomy preserves the record of this event, complete with evidence of massive water systems in the northern regions and intensive bombardment in the southern highlands. The geological scars from this ancient catastrophe extend across Mars' entire surface, creating features that continue to puzzle planetary scientists. Some of these features form patterns so massive and systematic that they can only be explained by forces operating on a planetary scale. Valles Marineris, the smoking gun. The most dramatic evidence of these planetary scale forces appears carved directly into Mars' surface. Valles Marineris cuts across Mars like a massive wound that never healed. This canyon system stretches 2,500 miles from east to west and plunges 4 miles deep in some sections. To put that in perspective, you could fit the entire Grand Canyon inside just one small section of Valles Marineris and still have room left over. The canyon is so large that if you placed it on Earth, it would stretch from New York to Los Angeles. For decades, planetary geologists have struggled to explain how this enormous canyon formed because Mars doesn't have the tectonic plate activity that creates large canyon systems on Earth. Earth's Grand Canyon formed over millions of years through river erosion combined with tectonic uplift that gradually exposed deeper rock layers. Mars doesn't have flowing rivers today, and it lacks the active tectonic processes that drive canyon formation on Earth. Mars' interior is essentially geologically dead, with no plate tectonics, no active volcanism outside of a few isolated regions, and no significant crustal movement. Valles Marineris remains a mystery among planetary scientists. Current Hypotheses include crustal rifting and collapse over an ancient water-saturated crust, but no definitive mechanism has been confirmed. The canyon doesn't follow the random path you'd expect from simple impact cratering or basic volcanic activity. Instead, it follows a systematic pattern that cuts across Mars' equatorial region in ways that standard geological processes struggle to explain. The 2025 Geological Survey missions used ground-penetrating radar and high-resolution orbital imaging to map the canyon system in unprecedented detail. The canyon structure reveals complex geological processes that operated on scales far beyond normal planetary geology. The canyon walls display layered rock formations that indicate sustained geological activity over millions of years. These aren't the simple impact scars or volcanic features that characterize most Martian surface geology. Mineral analysis of rock samples from the canyon walls reveals sedimentary layers that form through sustained water activity over geological time periods. The canyon contains thick deposits of sandstone, mudstone, and other sedimentary rocks that form when water carries particles and deposits them in layers. These aren't the thin, irregular deposits you get from occasional flooding or temporary lakes. The sedimentary sequences in Valles Marineris are hundreds of meters thick and show regular, rhythmic layering that forms when water flows consistently over millions of years. The rock layers also contain specific mineral formations that develop in deep, permanent water bodies. Geologists have identified iron oxide bands, sulfate deposits, and clay minerals that require sustained underwater conditions to form. These minerals don't form in temporary water bodies or from surface runoff. They require deep, stable water environments that persist over geological timescales. The presence of these minerals throughout the canyon walls indicates that Valles Marineris was carved by persistent water activity rather than surface erosion. Erosion patterns along the canyon walls show evidence of directional water flow that persisted for extended periods. The canyon walls display systematic erosion patterns that indicate sustained water movement in consistent directions. These patterns suggest that whatever water systems carved Valles Marineris operated according to organized flow patterns rather than random flooding or chaotic water movement. The canyon's dimensions and location correspond to computer models of large-scale water systems operating on Mars during periods when the planet had different environmental conditions. When researchers model Mars with thicker atmosphere, higher temperatures, and extensive water coverage, the predicted erosion patterns match the actual structure of Valles Marineris. The models suggest that the canyon formed when Mars had environmental conditions that could support large-scale water circulation systems. The canyon system includes numerous tributary channels that branch off from the main canyon in patterns that suggest systematic water flow. These tributaries don't show the random branching you'd expect from surface water runoff. Instead, they follow geometric patterns that indicate organized water circulation systems operated across large regions of Mars' surface during the canyon's formation period. Recent analysis of the canyon floor has revealed preserved sections of what appears to be ancient sedimentary deposits. These sediments contain chemical signatures that indicate formation in water-rich environments. The sediments also show layering patterns that suggest deposition over extended time periods in stable water bodies. The chemical composition of these deposits provides evidence that Mars once supported environmental conditions capable of sustaining large water systems. Magnetic field measurements around Valles Marineris show anomalies that indicate the canyon formed during a period when Mars had a stronger magnetic field than it does today. The magnetic signature suggests that the rocks in the canyon walls were magnetized when they formed, indicating that Mars had an active magnetic dynamo during the period when the canyon was being carved. This magnetic field evidence supports theories that Valles Marineris formed when Mars was more geologically active than it is today. Crater counting analysis shows that Valles Marineris is much older than most surface features on Mars, dating to approximately 3.5 billion years ago. This timing corresponds to a period when Mars had different environmental conditions than it does today. The canyon's age provides evidence that it formed during an earlier phase of Mars' geological history when the planet supported processes that no longer operate today. The geological evidence preserved in Valles Marineris indicates that Mars once experienced environmental conditions dramatically different from its current state. The canyon preserves a record of large-scale water systems, active geology, and sustained erosion processes that operated when Mars had a thicker atmosphere and stronger magnetic field. The scale and systematic nature of the canyon suggests that Mars once supported planetary-scale processes that fundamentally altered its surface geology. But Valles Marineris isn't the only evidence that Mars experienced catastrophic changes in its past. The planet's atmosphere itself contains traces of events that may have contributed to Mars' transformation. The nuclear isotope evidence. Atmospheric analysis provides another crucial piece of the puzzle about Mars' dramatic transformation. The Mars Atmospheric and Volatile Evolution mission has been sampling Mars' thin atmosphere since 2014. But the 2025 analysis revealed isotopic signatures that help scientists understand how Mars lost most of its original atmosphere. Mars contains unusual xenon isotope ratios that differ significantly from other planets in our solar system, providing clues about the atmospheric loss processes that stripped away Mars' once thicker atmosphere. Xenon isotope ratios measured by MAVEN help scientists track atmospheric loss over eons, but no credible evidence supports nuclear detonation origins for these measurements. The xenon signatures indicate that Mars experienced massive atmospheric escape events that removed most of its original atmosphere over geological time periods. When lighter isotopes escape to space more readily than heavier ones, they leave behind characteristic isotopic signatures that can be measured and analyzed. Mars' current xenon ratios show evidence of preferential loss of lighter isotopes, indicating that the planet's atmosphere was once much denser than it is today. The atmospheric loss mechanisms that affected Mars operated on planetary scales over millions of years. Solar wind stripping occurs when charged particles from the Sun interact with the planet's upper atmosphere and gradually remove atmospheric gases to space. Mars lacks the strong magnetic field that protects Earth's atmosphere from solar wind stripping, making it vulnerable to continuous atmospheric loss. Computer models show that solar wind stripping alone could account for the loss of a substantial Martian atmosphere over geological time periods. Impact. Erosion represents another mechanism that could have contributed to Mars' atmospheric loss. Large asteroid or comet impacts can blast atmospheric gases into space, particularly when the impacts occur at high velocity. The heavy bombardment period that affected all inner planets approximately 4 billion years ago would have subjected Mars to numerous large impacts capable of removing significant portions of its atmosphere. The combination of impact erosion and solar wind stripping provides a comprehensive explanation for how Mars transformed from a world with a thick atmosphere to the thin atmosphere planet we observe today. Isotopic analysis of noble gases in Mars' atmosphere reveals the timeline and intensity of atmospheric loss events. Argon isotope ratios indicate that Mars lost most of its atmosphere relatively early in its history, within the first billion years after formation. The noble gas signatures suggest that atmospheric loss occurred through multiple mechanisms operating simultaneously rather than a single catastrophic event. This gradual atmospheric stripping process would have fundamentally altered Mars' climate and surface conditions over geological time. The atmospheric isotope data correlates with evidence from Mars' surface geology that indicates the planet once supported much different environmental conditions. Mineral formations that require liquid water to form are found throughout Mars' surface, indicating that the planet once had temperatures and atmospheric pressure sufficient to maintain liquid water on its surface. The atmospheric loss that removed Mars' protective atmosphere would have made it impossible for liquid water to remain stable on the planet's surface. Comparative atmospheric analysis between Mars and other planets helps scientists understand the factors that determine atmospheric retention. Venus, despite being closer to the Sun, maintains a thick atmosphere because of its strong greenhouse effect and lack of significant atmospheric escape mechanisms. Earth retains its atmosphere through magnetic field protection and gravitational retention of atmospheric gases. Mars' smaller size, weaker gravity, and lack of magnetic field protection made it particularly vulnerable to atmospheric loss processes that other planets could resist. The timing of Mars' atmospheric loss corresponds to other major changes in the planet's geological activity. Mars' magnetic field shut down approximately 4 billion years ago, coinciding with the period when atmospheric loss accelerated. The loss of magnetic field protection exposed Mars' atmosphere directly to solar wind stripping, dramatically increasing the rate of atmospheric escape. This timing suggests that Mars' geological evolution and atmospheric evolution were closely linked through processes that affected the planet's magnetic field generation. Recent measurements by the MAVEN spacecraft have quantified the current rate of atmospheric loss from Mars. The spacecraft detects approximately 100 grams of atmospheric gas escaping to space every second, demonstrating that atmospheric loss continues today at measurable rates. While this current loss rate is much lower than the rates that operated during Mars' early history, it shows that the processes responsible for Mars' atmospheric transformation continue to operate. The atmospheric isotope evidence provides crucial context for understanding Mars' surface features and geological history. The planet's current thin atmosphere cannot support the liquid water systems that carved features like Valles Marineris and created the extensive sedimentary deposits found throughout Mars' surface. The atmospheric loss that transformed Mars from a potentially habitable world to its current state helps explain why the planet's surface preserves evidence of ancient water activity but shows no signs of current hydrological processes. Understanding Mars' atmospheric evolution has implications for assessing the planet's potential for past life and future human exploration. The atmospheric loss that stripped away Mars' protective atmosphere would have made the planet's surface increasingly hostile to life over geological time. However, the isotopic evidence indicates that Mars maintained a thicker atmosphere for hundreds of millions of years after formation, potentially providing sufficient time for life to develop and evolve on the planet's surface. The atmospheric isotope signatures preserved in Mars' thin atmosphere serve as a record of the planet's transformation from a world that might have supported life to the barren landscape visible today. These chemical fingerprints complement the geological evidence found across Mars' surface, building a comprehensive picture of how planetary-scale processes reshaped an entire world. The combination of atmospheric and geological evidence points to Mars having experienced changes so fundamental that they altered every aspect of the planet's environment, leaving behind traces that continue to puzzle scientists studying high-resolution images of the planet's surface features. Ancient structures and geometric anomalies. These high-resolution orbital surveys have captured surface features that initially appeared to challenge conventional understanding of Martian geology. The 2025 orbital imaging missions used synthetic aperture radar and multispectral analysis to photograph Mars at resolutions never achieved before. These surveys cataloged surface formations that sparked intense scientific debate about the processes that shaped Mars' landscape. The Mars Reconnaissance Orbiter's detailed imaging of the Cydonia region has provided definitive analysis of the famous face on Mars that captured public imagination for decades. When photographed at low resolution and specific lighting angles, the Mesa Formation in Cydonia creates shadows that resemble facial features. However, high-resolution imaging reveals that the face is a natural rock formation created by standard erosion processes operating over millions of years. The apparent facial features disappear when viewed from different angles or under different lighting conditions, demonstrating how pareidolia, the tendency to perceive meaningful patterns in random information, can create compelling illusions from natural geological features. Similar pareidolia effects explain many other formations that initially appeared artificial. The human brain evolved to recognize faces and geometric patterns as survival mechanisms, making us naturally inclined to see intentional design in random natural formations. Mars' unique erosion patterns, created by wind, ancient water flow, and temperature cycling, can produce formations that superficially resemble constructed features when viewed under specific conditions. The European Space Agency's orbital surveys have documented genuine geological curiosities that demonstrate Mars' complex formation history. The spider-like patterns discovered in Mars' polar regions initially appeared mysterious but proved to result from seasonal carbon dioxide sublimation processes. During Martian spring, carbon dioxide ice sublimes directly from solid to gas, creating pressure that carves radial channel patterns into the surface. These spiders form through completely natural processes but create geometric patterns that can appear artificial when viewed without understanding their formation mechanism. Ground-penetrating radar systems have detected subsurface density variations that reflect Mars' complex geological history rather than artificial construction. The Mars InSight lander's seismic monitoring equipment detected subsurface structures that initially seemed anomalous but proved consistent with natural geological processes. These subsurface features include lava tubes, collapsed caverns, and sedimentary layers that formed through volcanic activity and water erosion over geological time periods. Spectroscopic analysis of surface formations reveals mineral compositions that match natural Martian geology rather than artificial materials. The phyllosilicate minerals detected across Mars' surface formed through water-rock interactions over millions of years. These clay minerals create distinct spectral signatures that orbital instruments can detect and analyze. The mineral compositions found in apparently geometric formations match the surrounding natural geology, indicating formation through standard geological processes rather than artificial construction. The precision of some natural formations can exceed human expectations for random geological processes. Crystalline structures, sedimentary layering, and erosion patterns can create remarkably regular geometric shapes through purely natural mechanisms. Salt crystal formation creates perfect geometric shapes including cubes, hexagons, and other regular polygons. Sedimentary rock layers form parallel lines and regular patterns when deposited in stable water environments. Erosion along natural fracture lines creates straight edges and angular features that can appear artificially constructed. Thermal imaging reveals that surface formations maintain temperatures consistent with their mineral composition and exposure to solar radiation. Rocks with different mineral compositions absorb and radiate heat at different rates, creating thermal variations that correspond to geological rather than artificial factors. Dark volcanic rocks absorb more solar energy than light-colored sedimentary rocks, creating temperature differentials that reflect natural material properties rather than artificial heat sources. Magnetic field measurements around apparent geometric formations show magnetic signatures consistent with natural Martian geology. Mars crustal rocks contain iron-bearing minerals that create magnetic anomalies based on their formation history and mineral composition. These magnetic signatures reflect the geological processes that form the rocks rather than artificial magnetic materials or constructed features. The distribution of unusual surface formations follows patterns consistent with Mars' geological history and environmental conditions. Formations that initially appeared systematically placed actually correspond to geological features like ancient shorelines, volcanic activity zones, and impact crater patterns. The apparent geometric relationships between distant formations reflect the underlying geological processes that shaped Mars' surface rather than coordinated construction activities. Computer analysis of formation measurements reveals that apparent geometric precision falls within the range of natural geological variation. When measured with sufficient precision, natural formations display the angular relationships and proportional dimensions that can appear artificially precise. However, these measurements remain consistent with the precision achievable through natural crystallization, erosion, and sedimentation processes operating over geological time periods. Advanced imaging analysis has revealed that many formations contain surface details that become visible only at extremely high resolution. These details include natural fracture patterns, erosion channels, and mineral deposits that form through standard geological processes. The patterns follow the physical laws governing rock formation, weathering, and erosion rather than systematic design principles that would indicate artificial construction. The scientific consensus supports natural formation processes for all documented Martian surface features. While Mars displays remarkable geological complexity that reflects its dynamic formation history, no credible evidence supports artificial construction of surface features. The planet's geological record preserves evidence of volcanic activity, water erosion, impact cratering, and atmospheric processes that adequately explain all observed surface formations. Mars' geological complexity stems from its unique formation history and environmental evolution rather than artificial modification. The planet experienced geological processes that differ from Earth's current geology, creating surface features that can appear unusual when compared to terrestrial formations. However, these features remain consistent with natural planetary geology operating under Mars-specific environmental conditions. The search for evidence of past life on Mars continues through analysis of subsurface environments where conditions might have been more favorable for biological processes. Recent cave exploration missions have begun investigating Mars' underground environments, where protection from surface radiation and more stable temperatures might have preserved evidence of ancient biological activity. The giant civilization theory. While these underground environments offer tantalizing possibilities for discovering traces of ancient life, the search for evidence of past civilizations on Mars has taken researchers in unexpected directions. Recent rover missions have documented geological features that provide genuine insights into Mars' potentially habitable past, though the reality proves more subtle than sensational claims might suggest. The 2025 Mars cave exploration missions have revealed fascinating geological formations that demonstrate Mars once supported environments where life could potentially have existed. Deep inside lava tubes that provided natural shelter from radiation and harsh surface conditions, robotic explorers discovered mineral formations that tell the story of ancient water activity. These underground environments preserve geological records that surface erosion has destroyed elsewhere on the planet. Gypsum veins up to 1 centimeter wide snake through cave walls throughout these underground systems. Gypsum forms when sulfate-rich water evaporates, leaving behind crystalline deposits that preserve chemical signatures of the water that created them. The width and distribution of these gypsum veins indicate that substantial amounts of water flowed through Mars' underground cave systems for extended periods. The mineral composition of these deposits provides evidence that Mars once had active hydrological cycles that could transport dissolved minerals through underground water systems. Clay mineral evidence discovered throughout the cave systems reveals that Mars experienced prolonged periods of water-rock interaction under conditions that could have supported microbial life. These phyllosilicate minerals form when water chemically alters volcanic rocks over thousands of years, creating clay deposits that preserve information about ancient environmental conditions. The specific types of clay minerals found in Mars caves indicate that water remained in contact with rock surfaces long enough to create substantial chemical changes, suggesting stable water systems rather than brief flooding events. Sedimentary deposits within the cave system show layering patterns that indicate regular water flow and deposition cycles over geological time periods. These sedimentary layers contain organic carbon compounds that could represent either biological activity or abiotic chemical processes. The organic compounds are preserved within mineral matrices that protected them from degradation over millions of years. While these organic materials don't prove the existence of life, they demonstrate that Mars' ancient environments contained the chemical building blocks necessary for biological processes. The cave environments also preserve evidence of hydrothermal activity that could have provided energy sources for potential microbial ecosystems. Mineral deposits around ancient hot springs show chemical signatures that indicate water temperatures and chemical compositions suitable for extreme fuel organisms. These hydrothermal systems would have created localized environments where life could potentially survive even as Mars' surface conditions became increasingly hostile. Temperature measurements within the cave systems reveal that underground environments maintain more stable conditions than Mars' surface. The caves provide natural insulation from temperature extremes and protection from radiation that would be lethal to most forms of life. These stable underground conditions could have served as refugia where life might have persisted even after Mars' surface became uninhabitable. Chemical analysis of cave atmospheres shows trace gases that could indicate ongoing geological processes or potentially even biological activity. While most of these gases can be explained through abiotic chemical reactions, their presence demonstrates that Mars' underground environments remain chemically active. The detection of methane in some cave systems has generated particular interest because methane can be produced by both geological processes and biological activity. Ground-penetrating radar surveys have mapped extensive networks of underground caverns and tunnels that extend far beyond the caves currently accessible to robotic explorers. These underground systems create vast networks of potentially habitable environments that remain largely unexplored. The scale of these underground networks suggests that Mars contains substantial subsurface environments where conditions might have remained suitable for life long after the surface became uninhabitable. Mineral analysis of cave deposits reveals that Mars' underground water systems transported and concentrated elements essential for life, including phosphorus, sulfur, and nitrogen compounds. These elements accumulated in specific locations within the cave systems, creating chemical environments that could have supported complex biochemical processes. The concentration and distribution of these essential elements provides evidence that Mars' ancient underground environments contained the chemical ingredients necessary for life. The preservation of organic compounds within Mars cave systems demonstrates that the planet's underground environments can protect complex molecules from degradation over geological time periods. This preservation potential means that if life ever existed in Mars' underground environments, evidence of that life might still be recoverable from cave deposits. The discovery of preserved organic materials encourages continued exploration of Mars' subsurface environments as the most promising locations for finding evidence of past life. Recent analysis of cave mineral deposits has revealed isotopic signatures that provide information about the temperature and chemical conditions under which these minerals formed. These isotopic measurements indicate that Mars' underground water systems operated under conditions that could have supported thermophilic organisms similar to those found in Earth's deep subsurface environments. The isotopic evidence suggests that Mars' underground environments remained habitable for extended periods even as surface conditions deteriorated. The geological evidence preserved in Mars cave systems provides the most compelling case for the planet's past habitability. While no definitive proof of life has been discovered, the underground environments contain all the chemical and physical conditions necessary for life as we understand it. The caves preserve a record of Mars' transition from a potentially habitable world to its current state, documenting environmental changes that occurred over millions of years. These discoveries about Mars' underground environments have prompted scientists to reconsider not just the planet's geological history, but also the possibility that knowledge of Mars' past might have been preserved in ways that extend beyond purely geological evidence. The remarkable consistency of certain details about planetary catastrophe and ancient civilizations across human cultures has begun to attract scientific attention, particularly as Mars exploration continues to reveal evidence of the planet's dramatic transformation from a potentially habitable world to its current barren state. Correlation with ancient Earth texts. Human cultures have long speculated about Mars and its role in cosmic events, but no credible historical records match the specific findings emerging from modern scientific exploration. While ancient civilizations developed rich mythologies about celestial bodies and cosmic catastrophes, these stories reflect humanity's natural tendency to create explanatory narratives for phenomena they couldn't understand rather than preserve memories of actual events. Archaeological and anthropological research shows that ancient cultures worldwide developed creation myths and cosmic battle stories as ways to explain natural disasters, celestial movements, and other phenomena that exceeded their scientific understanding. These mythological frameworks served important cultural functions, providing explanatory models for cosmic events and establishing cultural identity through shared narratives about humanity's place in the universe. The development of these mythological systems followed predictable patterns based on observable celestial phenomena. Ancient cultures could observe Mars' distinctive red color, its variable brightness, and its retrograde motion across the sky. These observable characteristics naturally inspired stories about a wandering red star, a world in conflict, or a celestial body associated with war and destruction. The consistency of these themes across different cultures reflects shared human responses to the same observable astronomical phenomena rather than preserved historical memories. Modern comparative mythology demonstrates that similar stories develop independently in isolated cultures when they encounter similar environmental challenges or observable phenomena. The appearance of giant beings in various cultural traditions reflects common human psychological tendencies to create larger-than-life figures in explanatory narratives. These archetypal figures serve narrative functions in cultural storytelling rather than representing historical accounts of actual beings. The mathematical and astronomical knowledge found in some ancient texts reflects the sophisticated observational capabilities that developed in various civilizations over centuries of careful skywatching. Ancient astronomers achieved remarkable precision in tracking celestial movements and calculating cosmic cycles through dedicated observation and mathematical analysis. However, this astronomical knowledge developed through empirical observation of actual celestial phenomena rather than inherited memories of cosmic catastrophes. Archaeological evidence shows that ancient civilizations developed impressive architectural and engineering capabilities through gradual technological advancement and accumulated knowledge passed down through generations. The construction techniques used in megalithic structures reflect human ingenuity and organizational capability rather than intervention by beings from other worlds. The mathematical precision found in ancient monuments demonstrates the sophisticated understanding that human cultures developed through centuries of accumulated knowledge and practical experience. Genetic analysis of ancient human populations reveals the normal range of human physical variation that occurs naturally through evolutionary processes and population migration patterns. While some ancient populations showed distinctive physical characteristics, these variations fall within the expected range of human genetic diversity rather than indicating hybridization with beings from other worlds. The archaeological record shows continuous human cultural development through gradual technological advancement rather than sudden knowledge transfer from external sources. The interpretation of ancient text requires careful consideration of translation challenges, cultural context, and the symbolic language used in mythological narratives. Many apparent technical descriptions in ancient texts reflect metaphorical language used to describe natural phenomena or cultural concepts rather than literal technical specifications. Modern translation techniques reveal that apparent technical precision in ancient texts often results from interpretive bias rather than actual technical knowledge. Cultural transmission studies show how stories change and acquire new details as they pass through different cultures and time periods. Mythological narratives naturally accumulate elements from different sources and adapt to new cultural contexts, creating apparent connections between unrelated stories. The similarities found in cosmic catastrophe myths across different cultures reflect common human narrative patterns rather than shared historical memories. The scientific method requires distinguishing between correlation and causation when evaluating apparent connections between ancient stories and modern discoveries. While ancient myths may contain elements that superficially resemble modern scientific findings, this correlation doesn't establish causal relationships or validate the historical accuracy of mythological accounts. Scientific validation requires empirical evidence that can be independently verified through multiple research methods. Modern space exploration provides unprecedented opportunities to test hypotheses about planetary formation and solar system evolution through direct observation and measurement. The evidence gathered through robotic missions, orbital surveys, and laboratory analysis of planetary materials offers reliable data about cosmic processes that operated over geological time periods. This scientific evidence provides the foundation for understanding planetary evolution without requiring validation from ancient cultural sources. The distinction between scientific evidence and cultural speculation becomes crucial when evaluating claims about planetary catastrophes in ancient civilizations. While human cultures have always created explanatory narratives about cosmic events, these stories serve different functions than scientific hypotheses and require different types of evidence for validation. The scientific exploration of Mars provides empirical data about the planet's geological history that can be analyzed independently of cultural interpretations. The remarkable discoveries emerging from Mars exploration stand on their own scientific merit without requiring validation from ancient sources. The geological evidence of ancient water systems, atmospheric loss, and planetary-scale catastrophes provides compelling data about Mars' transformation from a potentially habitable world to its current state. This scientific evidence reveals a story of planetary evolution that exceeds the scope of any ancient mythological account. The real mystery lies not in correlating ancient stories with modern discoveries, but in understanding the actual physical processes that shaped Mars' dramatic geological history. The planet's unusual characteristics and evidence of catastrophic changes raise fundamental questions about planetary formation and evolution that require scientific investigation rather than mythological interpretation. The answers to these questions may reshape our understanding of how planetary systems develop and what forces can fundamentally alter entire worlds. Computer modeling and orbital mechanics analysis provide the tools necessary to investigate these questions through rigorous scientific methods. The Male-Deck connection. These scientific investigations have led some researchers to explore alternative theories about Mars formation, including proposals that challenge conventional planetary formation models. One less accepted theory suggests Mars was once a moon of a planet termed Male-Deck whose disruption may have seeded the asteroid belt. This remains controversial compared to the accretion model that most planetary scientists accept. The Male-Deck hypothesis emerged from attempts to explain several puzzling characteristics of our solar system's current configuration. Proponents of this theory point to the unusual distribution of mass in the inner solar system, where the asteroid belt occupies a region that mathematical models suggest should contain a substantial planet. They also note Mars' eccentric orbital characteristics and geological features that don't perfectly match standard planetary formation predictions. According to this speculative framework, Mars originally functioned as a large moon orbiting a planet positioned approximately where the asteroid belt now exists. The parent planet, designated Male-Deck in this theoretical model, would have been substantially larger than Mars and capable of supporting a large satellite in stable orbit. Computer simulations can model how such a system might have operated, with Mars maintaining a tidally locked relationship to its parent planet while both bodies orbited the Sun. The theory suggests that some catastrophic event disrupted this hypothetical planetary system, destroying Male-Deck and ejecting Mars from its original orbit. The destruction of the parent planet would have created the debris field that now forms the asteroid belt, while Mars was thrown into its current solar orbit through gravitational interactions with Jupiter. This scenario attempts to explain both the existence of the asteroid belt and Mars' unusual orbital and geological characteristics through a single catastrophic event. Supporters of the Male-Deck hypothesis point to several pieces of circumstantial evidence that they argue support this scenario. Mars' eccentric orbit and variable axial tilt differ from the more stable orbital characteristics of planets that formed in their current positions. The planet's rapid atmospheric loss could be explained by the trauma of sudden orbital displacement from a stable gravitational system. The geological evidence of ancient catastrophic events on Mars might reflect the aftermath of losing its gravitational anchor. The timing correlations that some researchers claim to identify between Mars' geological disruptions and Earth's mass extinction events form another component of the Male-Deck theory. Proponents argue that debris from a destroyed planet would have created impact events throughout the inner solar system, potentially explaining some of Earth's major extinction boundaries. They point to mineral compositions in impact craters that they claim match materials found on Mars and in asteroid samples. However, the mainstream scientific community remains skeptical of the Male-Deck hypothesis for several fundamental reasons. The theory lacks direct observational evidence and relies heavily on circumstantial correlations that can be explained through conventional planetary formation processes. Standard accretion models can account for the asteroid belt's formation through failed planetary assembly rather than requiring planetary destruction. Mars' unusual characteristics, while noteworthy, fall within the range of variation expected in planetary formation processes. The orbital mechanics. Calculations that would support planetary ejection scenarios face significant challenges from established gravitational physics. Ejecting a Mars-sized object from a stable orbit would require energy inputs that exceed the capabilities of most proposed catastrophic events. Jupiter's gravitational influence, while substantial, operates according to well-understood orbital mechanics that make planetary capture scenarios extremely unlikely under most conditions. The isotopic evidence that mail deck proponents cite as supporting their theory can be interpreted through alternative explanations that don't require planetary destruction. Atmospheric loss mechanisms, impact events, and volcanic processes can account for the chemical signatures found in Mars' geological record without invoking catastrophic planetary disruption. The mineral compositions found in Earth's impact craters reflect the normal range of materials present in asteroids and comets rather than requiring exotic planetary core materials. Current asteroid belt research focuses on understanding how the region's current configuration developed through gravitational interactions and collisional evolution over billions of years. The distribution patterns of asteroids reflect the complex interplay between gravitational resonances, collisional fragmentation, and orbital migration processes that operate over geological timescales. These processes can explain the asteroid belt's current structure without requiring catastrophic planetary destruction. The search for evidence supporting or refuting alternative planetary formation theories continues through multiple research approaches. Spectroscopic analysis of asteroid compositions provides data about the materials that formed in different regions of the early solar system. Orbital dynamics studies help scientists understand how gravitational interactions shape the current configuration of planetary orbits. Geological analysis of planetary surfaces reveals information about the processes that operated during planetary formation and early evolution. Mars exploration missions continue to gather data that helps scientists understand the planet's formation history and geological evolution. The evidence emerging from these missions provides insights into planetary formation processes that can be tested against various theoretical models. While the mail deck hypothesis remains speculative, the ongoing investigation of Mars' unusual characteristics contributes to broader understanding of how planetary systems develop and evolve. The scientific method requires distinguishing between established evidence and speculative theories when evaluating proposals about planetary formation. While alternative theories like the mail deck hypothesis raise interesting questions about solar system evolution, they must be evaluated against the available evidence using rigorous analytical methods. The continuing exploration of Mars and the asteroid belt provides opportunities to test various formation scenarios against observational data. The implications of Mars' unusual characteristics extend beyond academic questions about planetary formation. Understanding how Mars developed its current geological and atmospheric features has practical importance for future exploration missions and potential human settlement. The planet's history of environmental change provides insights into planetary climate evolution that may be relevant to understanding long-term environmental processes on Earth. As Mars exploration continues to reveal new information about the planet's complex history, scientists are finding that some of the most significant discoveries are generating unexpected responses from space agencies and government organizations. The handling of recent Mars mission data has begun to raise questions about how much information about the planet's past is being shared with the public. The 2025 cover-up. Recent Mars exploration missions have generated unprecedented amounts of scientific data that challenge conventional understanding of planetary formation and evolution. The 2025 discoveries represent the most comprehensive analysis of Mars' geological history ever conducted, revealing evidence of processes that don't match standard planetary formation models. These findings have prompted intense scientific debate about how Mars developed its current characteristics and what forces shaped its dramatic transformation from a potentially habitable world to its current state. The clay mineral discoveries made by recent rover missions provide compelling evidence that Mars once supported extensive water systems for millions of years. These phyllosilicate deposits form through prolonged water-rock interactions that require stable environmental conditions over geological time periods. The distribution and composition of these clay minerals indicate that Mars experienced sustained periods of surface water activity that created chemical environments suitable for life as we understand it. The mineral signatures suggest that Mars maintained habitable conditions for much longer than previously thought. Interior structure analysis using seismic data has revealed unexpected layering patterns that don't match conventional planetary formation models. The low-velocity zones detected deep within Mars' crust indicate partially molten regions that shouldn't exist in a planet of Mars' size and thermal history. These structural anomalies suggest that Mars experienced formation processes that differ significantly from other terrestrial planets in our solar system. The seismic evidence points to internal characteristics that challenge fundamental assumptions about how rocky planets develop their internal architecture. Atmospheric isotope measurements have documented the massive scale of atmospheric loss that transformed Mars from a world with a thick atmosphere to its current thin atmosphere state. The xenon isotope ratios measured by orbital missions reveal that Mars lost most of its original atmosphere through processes that operated over millions of years. The isotopic signatures indicate that atmospheric escape mechanisms removed the protective atmosphere that would have been necessary to maintain liquid water on Mars' surface. This atmospheric loss fundamentally altered Mars' climate and surface conditions. The geological evidence preserved in features like Valles Marineris demonstrates that Mars once supported large-scale water circulation systems that carved massive canyon networks across the planet's surface. The canyon structure and mineral composition indicate formation through sustained water flow rather than simple impact cratering or volcanic activity. The sedimentary deposits within the canyon system preserve evidence of underwater deposition processes that operated when Mars had environmental conditions dramatically different from its current state. Mars' crustal dichotomy represents one of the most dramatic planetary features in our solar system, with the northern and southern hemispheres showing completely different geological characteristics. The northern plains display thin crust and evidence of extensive water coverage, while the southern highlands contain thick, heavily cratered crust packed with impact debris. This hemispheric division suggests that Mars experienced planetary-scale processes that affected the entire planet's geological development. The asteroid belt's composition and distribution patterns provide additional context for understanding the dynamic processes that shaped our solar system's current configuration. Spectroscopic analysis of asteroid materials reveals mineral compositions that indicate formation under conditions different from their current solar system positions. The orbital mechanics and chemical signatures of asteroid belt objects suggest that our solar system experienced more complex gravitational interactions during its formation than standard accretion models predict. Underground cave systems discovered by recent missions preserve the most pristine records of Mars' ancient environmental conditions. These subsurface environments contain mineral deposits, organic compounds, and geological formations that demonstrate Mars once supported conditions suitable for life. The caves provide natural protection from surface radiation and temperature extremes, creating stable environments where evidence of ancient processes remains preserved. The chemical signatures found in these underground systems indicate that Mars maintained habitable conditions in subsurface environments even as surface conditions became increasingly hostile. The integration of data from multiple Mars missions creates a comprehensive picture of planetary evolution that extends beyond Mars itself to broader questions about how planetary systems develop and change over time. The evidence suggests that Mars experienced environmental changes so fundamental that they altered every aspect of the planet's geology, atmosphere, and potential for supporting life. These changes occurred through processes that operated on planetary scales over millions of years. Computer modeling of Mars' orbital mechanics reveals instabilities that raise questions about how the planet maintains its current position in the solar system. Mars' eccentric orbit and rotational characteristics create gravitational interactions that should theoretically destabilize its orbital position over geological timescales. The planet's ability to maintain stable orbital mechanics despite these instabilities suggests it may have been influenced by gravitational forces that standard planetary formation models don't fully account for. The timing correlations between Mars' geological disruptions and changes in other solar system bodies indicate that our planetary system experienced coordinated changes that affected multiple worlds simultaneously. The evidence suggests that whatever processes transformed Mars also influenced the development of other planets and the current configuration of the asteroid belt. These correlations point to solar system-wide events that shaped planetary evolution through mechanisms that remain poorly understood. The scientific implications of these discoveries extend beyond academic questions about planetary formation to fundamental questions about the processes that shape planetary systems and determine their long-term stability. Mars serves as a case study in planetary evolution that demonstrates how worlds can experience transformations so complete that they alter every aspect of a planet's environment and potential for supporting life. The accumulated evidence from Mars exploration reveals a planet that carries the physical record of processes that fundamentally reshaped our solar system's structure and development. The geological scars, atmospheric signatures, and structural anomalies preserved on Mars document events that challenge conventional understanding of how planetary systems evolve and what forces can influence their long-term development. These discoveries force us to confront fundamental questions about Mars' place in our solar system's history. The 2025 seismic data reveals interior structures that don't match standard planetary formation models. The atmospheric isotope measurements document massive atmospheric loss that transformed Mars from a potentially habitable world to its current barren state. Clay mineral deposits prove Mars supported extensive water systems for millions of years. The crustal dichotomy shows evidence of planetary-scale catastrophic events that split Mars into two distinct geological hemispheres. The accumulated evidence paints a picture of a planet that experienced transformation so complete it altered every aspect of Mars' environment. Whether through gradual atmospheric loss, catastrophic geological events, or complex gravitational interactions with other solar system bodies, Mars carries the physical record of processes that fundamentally reshaped our planetary neighborhood. The real question isn't just how Mars became the world we see today, but what these discoveries reveal about the dynamic forces that continue to shape planetary evolution.